for the third time for his last talk. So please, Rémi.
So thank you again for the introduction and for the invitation. It's been a very nice school. And so today my goal will be to explain a bit of a geometry of elementary functions. So this, I defined them in the first course, in the first hour of the mini course, and it was these functions that are built like algebraic functions, but allowing precompositions by exponential and logarithm using the Janeiro theorem. Okay, so there's two things I'd like to describe about elementary functions. And the first one, I already tell you what it's about. I'm going to recall it's the theorem of Liouville. From 1833, which describes, so elementary functions, they are stable by composition, they are stable by derivation, but they are not stable by integration. And the theorem of Liouville really describes precisely this failure of elementary function to be stable by integration. So I'm going to phrase you a little bit less general version, which is only for algebraic function. So if you take an algebraic function, but you could start with an elementary function and modify a little bit the conclusion. Okay. Then if the primitive, if the integral of this function is elementary, then it has a very specific form. Okay, so this integral is given by a rational function of two variables applied to t and f of t, plus the sum, a weighted sum of logarithm of functions that are, again, rational functions of t and f of t. So ci's are constants, and the ri are rational functions of two variables. Okay. So there's two kinds of consequences of this theorem. The first example I want to give, which is done by Liouville and even Abel, and is that you can use this theorem to show that the elliptic integral, okay, is not an elementary function. Okay, so you have to assume some kind of non-degeneracy condition, which is that, if I remember correctly, it's 4a cubed plus 27b squared is not 0. Okay, and you can use also this theorem in the other direction to tell you that there's many elementary functions. For example, if you look at e to the power t, or log t, they are elementary functions, but they cannot be written in this form, so they are not primitive of algebraic function. Okay. So as I said, you can even write down using this theorem, which is an algorithm that tells you when the primitive of an algebraic function is an elementary function. So a second result that I want to describe, which is less famous than the result of Liouville, but also very interesting, is that elementary functions, they are also not stable by compositional inverse. Okay, if you take the compositional inverse of an elementary function, it's not always an elementary function. And there's a theorem of Rit. So the problem has also been studied by Liouville, but Liouville didn't give the full structural theorem. The structural theorem is due to Rit in 1925, yes. And it tells you when the compositional inverse of an elementary function is itself elementary. So it said that if you let f of t be an holomorphic function of one variable, and it tells you that if both f of t and the compositional inverse compositional inverse of f of t are elementary functions. Okay. Then you can write f of t as a composition where each phi I with a odd index is an algebraic function. Okay. And each phi I with even index is either the logarithm or the exponential. Okay. So as the theorem of Liouville, this tells you that basically the only reason why a function and a compositional inverse can be elementary is for the obvious reason. You see that if f of t is written like that, you can invert phi 1 of t because it's an algebraic function, so the compositional inverse will be an algebraic function. And the second one is either log of or exp. Both you can invert with the other, and you can do like that the whole f of t. So it's clear that the converse of this statement is clear, and it tells you that this is the only way a function and a compositional inverse can be elementary. So there's always some very simple examples. Okay, you know many functions like that. For example, cos t and the inverse of cos t, arc cosine of t, are two functions which are inverse of each other, and both are elementary. Okay, so if you write it explicitly, you have that cos t is equal to EIT plus E minus IT divided by 2. And if you want to write it as in the shape of a Ritz theorem, you have to write it like that. Plus 1 divided by e to the power IT divided by 2. Okay, so here phi 1 of t would be IT, phi 2 of t would be the exponential of t, and phi 3 of t would be t plus 1 over t divided by 2. Okay, and the formula for arc cosine of t, I already gave it to you. It's minus I log of t plus square root of t squared minus 1. And again, both functions can be written in this form. Okay, and the point of the theorem is to say that this is the only way. So you see, we can compute quite well with elementary function, and the question is how to explain this kind of very nice properties, nice algebraic property that I call geometric property. Maybe algebraic properties would be a better name of these functions. Okay, so yes. Okay, so my goal would be to explain these two results. So I will explain somehow a result that generalizes both results at the same time. So explain this result using the Arch-Shanuel theorem. I'm going to phrase it in a bit different way of computing the transcendence degrees. So I've stated like that in the first lecture. So you take the transcendence, but I made a mistake in the way I stated it at that point. So if you take a holomorphic function and you look at the transcendence degree of this holomorphic function and their exponential, okay, and you restrict the Q-linear dimension of this function f1 fp, it's always greater or equal to 0. Okay, you see that what I stated previously is that these functions are Q-linearly independent, then this is equal to p, and so this is equal to p. So we've proved that the transcendence degree over C is greater or equal to 1, so I'm computing the transcendence degree over C of t. Okay? In order to have a clear analog of the case of numbers, you have to work over C of t and not over C, like I wrote before. And so let me just say that everything I'm going to explain at that point is joint work with Jonathan Kirby. So who is a model theorist and a number theorist who works in the University of East Anglia. Okay. So the main definition, and this will be the only definition for model theory I'm going to show you, is that the idea is that we are going to work with a bigger class of function of elementary than the class of elementary functions, is that we are going to work with all functions satisfying the equality case in Arc's theorem. Okay. So this is a definition. So this is a definition that comes from model theory. So the definition for numbers was done by Zilber, and the definition for function, which is the one that I'm going to use, was done by Jonathan Kirby. And so it's an holomorphic function. So again, of one variable, the statement, there's a definition that makes sense for holomorphic functions of several variables, but I'm going to give you the definition for one variable, g of t, of one, so I'm writing g of t, so it means of one variable, is exponentially algebraic. Okay. If we can find holomorphic functions F1, Fp defined on some open set, defined on some non-empty open set of the domain of definition of g of t. So it is like the case of algebraic function, we allow the domain of definition to go down, so such that a function g of t is exponentially algebraic if we can find some holomorphic function f1 of t, fp of t, such that this function satisfies the equality case in Arc's theorem, such that the transcendence degree of these functions and their exponential over c of t minus the q linear dimension of these functions modulo c is actually equal to 0. Okay, so if you have this inequality which is valid for all holomorphic function, you only consider holomorphic function which makes the equality. Okay, and now I have to explain how these functions relate to g of t. Is that g of t is algebraic over this function, so satisfies a non-trivial algebraic equation, okay, of the form y to the power n plus a n minus 1 of t y to the power n minus 1 plus a1 of t y plus a0 of t is equal to 0. So there's a polynomial which vanishes for this function g of t, and the ai of t, where's the ai of t? So if I'm assuming that they are rational functions, I just get the concept of algebraic function, and so I'm allowing them to depend on the time variable t, but also on f1 of t, fp of t, and their exponential. Okay, and this is a rational function. Okay, so essentially what I'm doing is that I'm looking at all the tuple of functions that satisfy the equality case in the inequality given by Arc's theorem, and I'm looking at all algebraic combination of such functions, and these functions I'm calling them exponentially algebraic. Okay. So let me give you some examples, just to give you a feel about this definition. So the first is that it follows from the definition that any algebraic function is exponentially algebraic. Okay, so it contains all algebraic functions, but it contains much more than all algebraic functions. So let me give you an example. For example, if I take this function here, I'm taking one that I've computed beforehand. Okay, this is somehow what can be considered as a nasty example of an elementary function. Okay, and I'm going to prove you that this function is exponentially algebraic. And so the first thing I need to do is to choose my function f1, fp. Okay, so I'm going to choose f1 of t. So let's write, you write the cosine of t like e to the power it plus e to the power minus it divided by 2. And I'm going to choose f1 of t, which is I times t. Okay, because I want to be able to take the exponential, and so the exponential of f1 of t is e to the power it. Okay, when I have e to the power it, I also have e to the power minus it. Okay, but now I want to take the exponential of the cosine, so I'm going to add the function f2 of t, which is e to the power eit. Okay, so if I add, which is e to the power it, okay, and whose exponential is e to the power it. Okay, but I also want, because I want to make the cosine, I also want e to the power minus it. So I'm going to add a third function, which is e to the power minus it. And e to the power f3 of t is equal to e to the power minus it. Okay, and then I'm going to do a fourth function, which is to handle the logarithm part. I'm going to add the fourth function f4 of t, which is the log of the square root of 1 plus t squared, and e to the power f4 of t will be square root of 1 plus t squared. Okay. Now I want to count the number of algebraic relations between these functions and their exponential. I want to show that they satisfy an equality case in Axe theorem, so I want to count. So you have one algebraic relation, which says that f1 of t itself is an algebraic function, and you have another algebraic relation, which is here, which says that the function, this function e to the power f4 of t, is an algebraic function. Okay, you now, so this is one relation, this is two relation. Now I have one relation which tells me that e to the power f1 of t is equal to f2 of t. This is the third algebraic relation, and you see that this is independent from the previous relations that I considered. And I have a fourth algebraic relation, which says that the two functions are inverse of each other. So I have four independent algebraic relations between this function. Okay, so I have shown that the transcendence degree of f1, f4, e to the power f1, e to the power f4 is less or equal to 4, because I found four relations between them. Okay, but it's not hard to see that this, if you take q linear combinations of these four functions, you will never get a constant. Okay, so the linear dimension of q of these functions is equal to 0. Okay, but now using, is equal to 4. Okay, but now using Axe theorem tells me that it must be the case that the transcendence degree of this function and their exponential, so I should write computed over c of t, is equal to 4. Okay, so you see that this function, this definition is not that hard to handle in practice, because one inequality in I is given by Axe theorem. So you only have to show the other inequality, and to show the other inequality, you just have to guess sufficiently many algebraic relations. Okay, so this is an algebraic function, so it can be seen that g of t is in the algebraic closure of c of t, f1 of t, f4 of t, e to the power f1 of t, e to the power f4 of t alg, and therefore g of t is exponentially algebraic. Okay, so what makes this definition that you can compute in practice, it's really that you have one inequality that is done for you by Axe theorem, and therefore you only have to find enough relations between your functions. So I show you this example to avoid proving you a lemma that is a bit annoying to prove, and which Jonathan proved before, and which is that any elementary function is exponentially algebraic. Okay, so this can be done by induction, somehow on the number of time you pre-compose or post-compose by log and x, but you see that here I gave you somehow a complicated elementary function, and I show you by hand that this is exponentially algebraic. So what are the functions that are exponentially algebraic and that are not elementary? So here is another example, which is called Lambert function. Okay. And which is, so L of W, which is a local analytic inverse of the function which to z maps to z e to the power z. Okay, so in other words, you have, this is the solution of the functional equation that L of W times e to the power W is equal to W. Okay, and again, it's not hard to see that this function is exponentially algebraic. So this equation that I wrote here shows you that the transcendence degree of the Lambert function and this exponential. Okay, by definition, I wrote you one relation here, so this is less or equal to 1. And this function is not a constant, so it's Q-linear dimension of L of W over the constant is equal to 0. And again, you have the other inequality being given by Axe theorem, which implies that this is equal to 1. Okay, so implication using Axe theorem that L of omega is exponentially algebraic. Okay, this function is even an equality case itself in Axe theorem, and it follows from the result of RIT that I gave you before that this function is not elementary. Okay, you cannot write z times e to the power z as a composition of function that I wrote before, and Liouville already noticed that. And he showed in 1836 that this function is not elementary function. Okay. So if you think about the case of Axe-Chanuel theorem, it tells you that there are many functions that satisfy, so this is an example of a function that satisfies the equality case in Axe theorem, but which is not an elementary function. Okay, so there are more equality cases than the obvious one you can guess just by looking at the theorem, which is, okay, the algebraic functions give you equality case, then the exponential of algebraic function give you an equality case, but you also have functions which are neither algebraic function or exponential of algebraic function. And so just to give you a similar story, okay, so Liouville studies both the Lambert function and the Kepler's functions. So which appears even before, I think it's 1609, which is the solution of z minus e sine of z is equal to W. So it's a function k of W, which is a local analytic inverse of this function here, z minus e sine of z. And the notation is quite bad because E here in the mind of Kepler is the eccentricity of an ellipse. So this is a real number between 0 and 1, and it has nothing to do with the number e from the exponential. Okay. So something that one can prove, and was again done by my co-author, by Jonathan Kirby, is that actually the class of exponentially algebraic function is stable under local compositional inverse. Okay. So you see that it seems more natural to work, instead of working with elementary function, to work with this other class of functions, the class of exponentially algebraic function. The first reason is that they have a clear connection with the Arch-Chanuel theorem, and the second reason is that they are more general than elementary functions. They contain all elementary functions, but they are also stable under local compositional inverse, and so they are a good way to make sense of both Reed theorem and the Liouville theorem at the same time. Okay. So the main theorem I'm going to present is tells you when the solution of a linear differential equation can be an exponentially algebraic function. And so the theorem, which is done with Jonathan Kirby, tells you that so if you take an holomorphic function of one variable, okay, and you assume two different kind of hypotheses. So you assume that this function is exponentially algebraic. So in particular, this applies to all elementary functions. And the second thing that you assume is that f of t satisfies a non-trivial linear differential equation. Okay, so what I mean is that you have an equation L of the form y, so this is the nth derivative of y. Then you have the nth minus 1 derivative of y plus a1 of t, a0 of ty plus a minus 1 of t is equal to 0. So I'm taking a linear equation which is not necessarily homogeneous, right? You have a constant term. And the ai of t are algebraic functions. Okay. So this setup generalizes the case of Liouville theorem, because Liouville considers only equation of the form y prime is equal to a minus 1 of t. And here we have replaced taking the primitive of an algebraic function by solving a linear differential equation with coefficients are algebraic function. And so in that case, you can conclude that then the function f of t is an elementary function Okay, so you started by any exponentially algebraic function. So for example, the Lambert function will not satisfy any linear differential equation. The Kepler's function will also not satisfy any linear differential equation, but you can even say something substantial, which is substantial for elementary function, of a special form, okay, which is f of t is equal to s times log of R1 of t, log of Rs Rn of t, e to the power Rn plus 1 of t, e to the power Rn of t. Okay. So where the Ri of t, the R1 of t, Rn plus 1 of t are algebraic functions, and S is an algebraic function of n variable. Of n plus 1 variable. Okay, so you.
What did you write just after logarithm of Rn of t?
Logarithm of Rn of t,
Yes.
and then e to the power Rn plus 1 of t.
Yes. Till?
Yes, e to the power Rm of t. Okay, so I should put m's here. Okay, so essentially, you can write down explicitly the kind of solutions of elementary function. So it tells you that the lumber function doesn't satisfy any linear differential equation, the Kepler function doesn't satisfy any linear differential equation, and so does, for example, the function e to the power t, or log of log t. What I was telling you before is that they are not primitive of algebraic functions, but they are even not solutions of linear differential equations, because they are not of this shape. So let me just comment. Okay, is that Liouville's theorem deals with a particular case of equation, so it's y prime is equal to a minus 1 of t, okay, which is covered by this theorem, but the Liouville theorem, the conclusion is more precise. Okay. So in which sense the conclusion is more precise?
Excuse me again, but it seems that the Rn plus 1 doesn't appear in your formula.
The R
M plus 1.
Rm, yeah? Yeah, it's just until Rm, okay? Oh. It's just I wanted to index them all by the same number.
And n is the same n of the
No.
order of the differential
No.
operator? No.
Thank you.
Okay.
The number L here is S.
Okay. Thank you.
Okay, already in Liouville's theorem, you can see that the bound is 1 on the order of the equation, and you can need weighted sums of logarithm of arbitrary length. Okay, so Liouville's theorem deals with a particular case, but the conclusion is more precise. And there's two things that is more precise, is that in Liouville's theorem, it gives you an explicit, so S has an explicit form. Okay, and the second thing is that here, I concluded that so in the case of Liouville's theorem, it says that the Ri of t, I can write it as Si of the function of t. It's like if I could write the Ri of t as rational function of t and the coefficient of the equation. Okay, well, these are rational functions. So here I have to consider algebraic functions where, in the case of Liouville's theorem, everything reduced to rational functions. Okay? And the reason for that is because the Galois group of this equation that I wrote here is a subgroup of the additive group, and the additive group has no non-trivial finite subgroup. Okay? And this fact gives you that actually, in the case where you take an equation whose Galois group is connected, you can indeed assume that the R1 of t, Rm of t are actually rational function of the coefficient of your equations. Okay, but since in general you can have arbitrary finite group, you can have arbitrary algebraic functions appearing as a solution of a linear equation over C of t, at this level of generality you cannot improve, okay, this statement. Okay, you cannot get a rational function, but of course for computation, for giving an actual algorithm, this is still much weaker than the case of Liouville's theorem, because you have to consider arbitrary algebraic functions here. Okay, but you still recover many interesting examples. So for example, from this theorem, you can recover that this function is not elementary, the Airy function is not elementary, Bessel functions are not elementary. Okay, because they satisfy linear differential equations, and you can compute the Galois group of these linear equations and show that this is an obstruction to have a shape like that for the solution of your equation. So we still recover many examples, but as stated, the theorem doesn't recover the. So as stated here, I don't know how to recover. That this is not elementary. Okay, you have to make, I mean, here when I'm saying you recover is that you recover without any computations. Here you still have to do the same computations that were done by Uville, but there is a way to formulate these things in a bit more general way in model theory where you also recover this one. So you would recover all the classical examples of functions that are not elementary can be recovered using this theorem. Okay. So, okay. So,
in fact, you prove that they are not algebraic exponential.
Indeed, and in fact, we get more because we get that they are not even exponentially algebraic. So they cannot be the Lambert function or the Kepler functions or any combination of elementary functions with them. So indeed, we get more than the classical results. Okay, so what I want to try to explain you is not the proof of this theorem, but the proof of Uville's theorem, but not for elementary function, but for exponentially algebraic functions. Okay, so the proof of Uville's theorem for exponentially algebraic functions. So the proof of this theorem is not very different, but it's still a little bit more technical. So I want to explain the proof of Uville's theorem. Okay, but not for elementary function. We are going to do something a little bit better than what was done in 1833, okay, which is a good thing because we are in 2024. So we are going to do it for exponentially algebraic function. Okay, so I'm going to go back to the setting I was using for the proof of Axe theorem. So I'm going to make a construction. So as I explained, the idea about this exponentially algebraic function is that it's really about studying the equality case in the Axe-Annual theorem. So we have this algebraic variety, which is a tangent space to the multiplicative group to the power n, which is the product of these two groups. Okay, and the coordinates here are always written y1, yn. And the coordinate on the additive group, x1, xn. So we have the exponential foliation, which is defined by the omega I, which are the dyi divided by yi minus dxi. Okay? And now we are taking z, a closed subvariety, okay, irreducible subvariety of x. And since I want to study the equality case in Axe theorem tells me that, okay, if this intersection with f is typical and constrained, then the dimension is greater or equal to n plus 1. And so I'm going to fix that the dimension of z is equal to n plus 1. Okay, this is where I'm saying that I'm really looking at things which make the equality case with Axe theorem. Okay, and I'm making one hypothesis. The hypothesis is that the intersection between z and f is typical and not constrained. And constrained. Okay, so what does that mean? It means in this setting, because we have fixed the dimension of Z, that the codimension in Z of the restricted foliation, okay, is 1. Okay, this is the code, this is 1. This is n, sorry. Okay, which is the same thing as the codimension of F. Okay, and this tells you so that the rank or the dimension of F restricted to Z is equal to 1. Okay, so the exponential foliation restricts to a foliation by curve on Z. And the second thing that this hypothesis tells me is that this foliation has no rational integrals. Okay. So this is the data for my construction, and the lemma, I need to write it upstairs. And the lemma tell me the following thing. So I'm going to fix t, let t be a rational function on Z, which is not constant, which is not in C. Okay. So then there is a unique derivation. There is a unique derivation, okay, partial, which lives on Z and is trivial on C with the following properties. The first thing that I'm going to assume is that delta of T has to be sent to 1. So T generates a differential subfield of this C of Z with this derivation. And the second thing is that if I apply the interior product by this derivation to the eta I, it's equal to 0, where eta I, this is the pullback of the eta i's are the one form which defines the foliation F restricted to Z, so which are the pullback of the omega I. Okay. So the proof of the lemma is very easy. So first, we may replace Z by an open set. So we may assume that this one form are really generating the foliation on Z. Okay, and because f of Z has no rational integral, okay, it will tell me that the function T implies that the function T is generically transverse in the weak sense to the foliation F restricted to Z. Okay, so I don't mean that the generic fiber of this map is transverse to the restricted foliation, but I mean that on an open set of up to throwing points in Z, the foliations that I get will be transversal to the foliation after throwing out all possible points in Z, not only after throwing points in A1. Okay. So we get an exact sequence. So the exact sequence, I'm going to write like that, 0 omega 1 of C of T divided by C tensor C of T C of Z, omega 1 of C of Z over C, omega 1 of C of Z over C of T. Okay, so this is an exact sequence of C of Z vector spaces. Okay, splits. Okay, so telling that this thing is generically transversal, it means, so here I'm really working at the generic point of Z, and it means that this space of one form, So I can write it as, so this object is generated by dt, so by the span C of z of eta 1, eta n, plus, omega 1 of C of t over C tensor C of t, C of z. And this object is just generated, so this is a one-dimensional C of z vector space. So this is just C of z dt. Okay, so what this tells me, this is the dual of the space of derivation, and so that giving a derivation is uniquely determined by giving the value, the interior product of the derivation with eta 1, eta n, and the interior product with dt. Okay, and the first part here tells me that the interior product with dt is equal to 1. Okay, and this gives me the interior product with the eta I, and therefore this completely characterizes, this condition characterizes a unique derivation. Okay. And so this object, so I'm checking how much time I have left. So this object, so a differential field of the form so C of z alg divided by C of t, okay, and where equipped with the derivation given by the previous lemma, is called an exponentially algebraic differential field extension. Okay. Okay. So let me make the connection now between the two setups. And so this is the proposition that allows you to compute geometrically with exponentially algebraic function. And it's somehow a characterization of a differentially algebraic function. So if you take, let f of t be an holomorphic function, okay, so what does that mean? That f of t is exponentially algebraic. It's equivalent to say that the differential field generated, so this is a notation for the differential field generated by f of t over C of t, is isomorphic to a differential subfield of a field of this form. It's isomorphic to a differential subfield of the set of this form. So the differential field, let me think about them as a differential field extension. Homomorphic to a differential. And so you can see that by using this kind of procedure, you can, for example, produce subvariety Z such that this differential field will be very complicated in the sense that it will not have any intermediate differential subfields, not trivial. And in this form, you can produce functions which are exponentially algebraic, but which are very far from being elementary functions. Okay. So I'm not going to prove this proposition. It's essentially a restatement of the definition. And so now here is the proof. So how much time do I have left? No? Okay, so let me just explain that. So this is the key idea for the proof of Liouville's theorem. So what you're going to do is that you start with this definition. So in the proof of Liouville's theorem, okay, you're going to start by including, so you start with a function, you start with a g of t, which is the integral of f of t dt Okay, and you're going to assume that this function is elementary so that you can embed the differential field generated by g of t inside the differential field of this form. So this is the same thing as the field generated by f of t and g of t inside the form, a differential field of the form c of t alge. Okay. And you are going to write the same exact sequence I was writing before. I'm going to stop very fast. Okay, and you're going to write the same exact sequence. Omega 1 of C of Z alge. Oh, I should put, yeah, I put the algebraic closure here over C of T and omega 1 of C of Z alge over C of T, G of T. Okay, so I'm writing the similar exact sequence, but the extension of differential field is now given by C of T inside this field and inside this field. Okay, and by construction, okay, this eta 1 is going to be the span of my one form eta 1 eta n. Okay, by construction, this will be exactly the span of this one form eta 1 eta n. Okay, and all this one form, they all satisfy. So let me just write the key observation and I'll stop here. So the key observation is that all this one form, they vanish along the Lie derivative of the vector field, and so does the derivative of dg. Okay? And now you're going to use just the result that if you have this, because this eta 1, eta n are C-linearly dependent, they form a basis of the solutions of this equation, and therefore you can write dg as a C-linear combination of the eta I. Okay, and when you do that, then by using the same kind of argument that we use in the proof of actionable theorem, you're going to be able to prove that G is going to be, that you're going to be able to write dg. Okay, you're going to be able to conclude the proof. Okay. All right. And I'm
Thank you very
here
much.
because I have no more time.
So are there any questions?
Can you just repeat your notation for the differential field generated by f of t?
Here, this is so. This is the differential field generated by f of t over c of t. So this is c of t, f of t, f prime of t, and all derivatives. But you can see that so since this is finite dimensional, one consequence of this characterization is that exponentially algebraic functions, they are stable by derivation, and they are all differentially algebraic. This, you can read it directly from this proposition.
Thank you.
And the conclusion, so the conclusion of Liouville theorem in that case is the same conclusion that,
So what you're going to show is that
what is the conclusion here?
you're going to show that g of t, okay, so you assume that it's exponentially algebraic, and you're going to show that it's R0 of t f of t plus
so
the sum of ci log.
The conclusion is
Of-
the very same conclusion.
Yeah, it's the very same
okay.
conclusion. Okay, the statement of the theorem in the case of linear equation is less precise, but if you apply it in this specific case, you really find the same
Okay.
conclusion as
Now-
Liouville.
Other question here? George.
So any questions from this side? So I have one. Do you have a version of this result for Liouvillean functions, meaning Liouvillean function which is exponentially algebraic is like this and that?
No, I don't have a result for Liouvillean. So the case of Liouvillean function is, so from a Galois-theoretic perspective, it's easier because there's a clear Galois-theoretic connection for Liouvillean function, but I don't have the Ax-Shanuel theorem for Liouvillean function. The Ax-Shanuel theorem is really related to elementary function, and Liouvillean function, it's a bit different. So I don't know how to get the result for Liouvillean functions, but there are some results of Michael Singer which relate having a Liouvillean first integral to having Liouvillean solutions for linear differential equation of order 2. But this is somehow an analog of this relation between exponentially algebraic function and elementary function for elementary function. So this doesn't apply to Liouvillean function because there's no, I mean, there's not the Ax-Shanuel theorem that I'm using here.
Okay, thank you. Any other question or comment? Okay.
So, thank you. Let us thank again Rémi for his beautiful lectures. Thank you very much.
Okay, see you in 1 hour.
Yes.